Brute force and exhaustive search algorithms. I'm Efina and I'll be presenting you this topic. The topics of discussion in brute force approach are the selection sort and the bubble sort, and the topic of discussion in exhaustive search approach are the graph traversal algorithms, the breadth first traversal and the depth first traversal, then the traveling salesman problem and the knapsack problem. Brute force approach. It is a design strategy of the problem directly based on the problem statement. The intermediate solution are obtained considering the entire problem size. Examples: selection sort and bubble sort. Selection sort. Selection sort scans the entire unsorted part of the given list to find its smallest element and exchange as the next element in the sorted list at every iteration. That is, generally on the ith pass through the list, which we number from 0 to n-2, the algorithm searches for the smallest item amongst the last n-I elements and swaps it with a of I. The pictorial representation is as given here. In the first iteration marked as A, it finds the smallest element, which is 1, and swaps it with the element at index 0, and this is done at each iteration until the sorted array is obtained. Here is our algorithm for selection sort. It uses two nested for loops. The outer for loop with the I variable select the array index position where the current smallest element will be placed. The inner for loop with the j variable browses across each unsorted element in the array to find the smallest element. Algorithm analysis of selection sort. The for loop limits of the selection sort algorithm becomes the limit of the summation, and applying the summation formulas, we obtain the time complexity of the selection sort as big O of n squared. Bubble sort. Bubble sort compares adjacent element of the list and exchange them if they are out of order. That is, at the first pass, the largest element is pushed to the last position, n-1 on the list, and at the second pass, the second largest element is pushed to the position n-2 on the list, and so on. Given here is the pictorial representation of the first iteration of the bubble sort, where the largest element 8 is pushed to the last position by a ripple effect. Bubble sort algorithm. The algorithm uses a pair of nested for loops. The outer for loop with the I variable is for each iteration of the bubble sort, and the inner for loop with the j variable performs the ripple effect at each iteration, moving the largest element to its position. Algorithm analysis of bubble sort. Very similar to the selection sort, the bubble sort also takes the limits of the for loop as the limits of the summation, and the summation formulas are applied, and we obtain the time complexity of the bubble sort as big O of n squared. Exhaustive search. It is a brute force approach to combinatorial problems. Exhaustive search generates each and every solution for the problem and selects those of them that satisfy all the constraints of the problem. Then the final solution is the most optimal one. The examples of exhaustive search that are discussed in this presentation are the graph traversal algorithm, the traveling salesman problem, and the knapsack problem. Graph traversal algorithm, the depth first search. Every traversal algorithm of a graph performs two steps at each iteration. The first is visiting the vertex in the graph. The second is finding the next vertex by traversing along the edge of the graph. The depth first search starts the graph traversal at an arbitrary vertex by marking it as visited. On each iteration, the algorithm proceeds to an unvisited vertex that is adjacent to the one it is currently visited. The process continues until a vertex with no adjacent unvisited vertex is encountered. At the dead end, the algorithm backs up one edge to the vertex it came from and tries to continue visiting unvisited vertex from there. The algorithm eventually halts after backing up to the starting vertex, with the later being a dead end. Depth first graph traversal is performed in the given graph. The depth first graph traversal algorithm uses the stack data structure. The algorithm starts the traversal with the arbitrary vertex A. A is marked as visited and it is pushed as a content of the stack. The adjacent vertex of A, the B vertex, is marked as visited next and it is pushed as the content of the stack. B is a dead end, that is, it has no adjacent vertices. Hence, the top of the stack, which is B, is popped from the stack. Now the top of the stack is A. The unvisited vertex of A is visited now, which is S. S is marked as visited and it is pushed as the content of the stack. Then the adjacent vertex of S, C, is marked as visited and it is pushed as the content of the stack. Continuing with the example, vertex D is visited after the vertex C and it is pushed as the content of the stack. At vertex D, it becomes the dead end for traversal, and D, being the top of the stack, is popped from the stack. Now the top of the stack is the vertex C. The unvisited vertex adjacent to C is E, which is visited next, and it is pushed as the top of the stack. The unvisited vertex to E, H, is visited next and it is pushed as the top of the stack. The unvisited vertex to H, which is G, which is visited next and is pushed as the top of the stack. The unvisited vertex adjacent to G, which is F, is visited next and it is pushed to the stack. At F, there are no adjacent vertices that are unvisited. Hence, it is popped from the top of the stack. The next vertex at the top of the stack is G, and there is no unvisited vertex to G. Hence, it is also popped from the stack. Now the top of the stack is H, and at H there are no unvisited vertices, and it is popped from the top of the stack. Similarly for E, C, S and A. A being the starting vertex and the stack being empty, the depth first traversal considers all the vertices are traversed in the graph. Hence, the traversal order of vertices for the given example is the vertex A followed by B, S, C, D, E, H, G and F. The same procedure of depth first traversal is followed for directed graph, considering the direction of the edges. The depth first search algorithm. The graph G with the vertices V and edges E is the input to the DFS algorithm. The graph is represented using a adjacency matrix or a adjacency list. The output of the DFS algorithm is the graph G with its vertices marked with consecutive integers in the order of the DFS traversal. The arbitrary vertex that is selected initially is marked with the value 0 using the count variable. The traversal is performed recursively in the adjacent vertices, and the visited vertex are marked consecutively with the count. The time complexity of the depth first search algorithm is theta of V squared, where V represents the number of vertices in the graph. This time complexity is obtained when the input graph is represented as an adjacency matrix. Two important applications of depth first traversal is to find the connectivity in a graph and the acyclicity of the graph. Breadth first traversal or breadth first search. Similar to the depth first traversal, the breadth first traversal selects an arbitrary vertex to start the traversal. The BFS visits all the vertices that are adjacent to the arbitrary starting vertex. Then the BFS visits all the unvisited vertices adjacent to the currently visited vertices and proceeds likewise. When all the vertices are visited in the connected component of the graph, the BFS restarts at an arbitrary vertex from another connected component of the graph. Breadth first graph traversal. The breadth first graph traversal algorithm uses the queue data structure. Let us study the BFS procedure with an example. Consider the graph given in the figure, which has 9 vertices. Let us traverse the graph as BFS, starting at vertex A, resolving the ties between the vertices in alphabetical order. The table here will help us in the BFS traversal. The first column in the table represents the vertex that is visited at that particular instance of the procedure. The second column represents the vertex that is pushed into the queue at that instance, and the third column represents the vertex that is popped from the queue. The fourth column represents the queue content at that instance. Since we start the traversal from the vertex A, we push the vertex A into the queue. Now the queue content is A. Now we know that the vertices B and S are connected to A. We pop the vertex A from the queue and mark A as the visited vertex. Then the vertices that are connected to A, which are B and S, are pushed into the queue. Now the queue content is B and S. The front end of the queue contains the vertex B. As we can see in the graph representation, B is not connected to any other unvisited vertices. Hence, we pop B from the queue and mark B as visited. Now, the content of the queue is S. To S, C and G are connected, and these are the unvisited vertices. So, when we pop S from the queue, we mark S as the visited vertex and we push the unvisited connected vertices C and G into the queue. Now, the content of the queue are C and G. Now, we pop C from the queue, mark it as visited, and the unvisited vertices connected to C, which are the D, E, and F resolved in the alphabetical order, are pushed into the queue. G, which is in the front end of the queue, is popped from the queue and it is marked as visited, and the connected vertex H to G is included to the queue. Now D is in the front of the queue, but it has no unvisited vertex connected to it. D is marked as visited and it is popped from the queue. Similarly, E, F, and H. Now the queue is empty and all the vertices are visited. The traversal order of vertices using BFS for the given graph is A traverse to B, traverse to S, traverse to C, traverse to G, traverse to D, traverses to E, F, and then H. Note, similar to our DFS, the same procedure can be followed for BFS for directed graph also. But we have to consider the direction of the edges in the directed graph. Breadth-first traversal algorithm. The graph G with the vertices V and edges E is the input to the BFS algorithm. The graph G is represented as an adjacency matrix or an adjacency list. The variable count is used to mark when the vertices are visited. The BFS algorithm uses the queue to do the BFS traversal. The count variable is incremented and it is used to mark the visited vertex in the order of the BFS traversal. The time efficiency of the breadth-first traversal is theta of sum of the number of vertices and the number of edges. This efficiency is obtained when the adjacency list is used to represent the input graph G. Two important applications of the traversal algorithm is to find the connectivity in the graph and acyclicity of the graph. The knapsack problem. The inputs to the knapsack problem are n items of known weights w suffix 1 to w suffix n and their values v suffix 1 to v suffix n. A knapsack of capacity W is also given as input. The knapsack problem is to find the most valuable subset of item that will fit into the knapsack. The example of a knapsack problem is described pictorially. A knapsack of weight 10 is taken. The problem contains 4 items and each item has a weight and a value. The weight of item 1 is 7 and its value is $42. The weight of item 2 is 3 and its value is $12. The weight of item 3 is 4 and its value is $40, and the weight of item 4 is 5 and its value is $25. The knapsack problem is to find the subset of items that will fit in the knapsack and has the maximum value. Let us solve this knapsack problem using the exhaustive search approach. The exhaustive search approach to the knapsack problem finds every subset of item that will fit in the knapsack and selects the subset of items that has the maximum total value. The table given here illustrates the exhaustive search approach of the knapsack problem. The first column represents the subset of items selected. The second column represents the weight of the subset of items. The third column represents the total value of the subset of items selected. The total weight of the subset of items selected must not exceed 10 in the given example. If the total weight exceeds the value of 10, then the solution is not a feasible one. So, taking the first row in the table, when no items are selected, the total weight is 0 and the total value is 0. Taking the fifth row, where the subset of items 1 and 2 are selected, it has a total weight of 10 and total value of 54. When the items 1 and 4 are selected, it has a total weight of 12. And that is not feasible because the total weight of 12 will not fit into the knapsack of weight 10. When all the feasible solutions are found using the exhaustive search approach, the subset of items with the maximum weight is selected as the optimal solution. In this example, when items 3 and 4 are put in the knapsack with a total weight of 9, it has a value of $65. The algorithm analysis for exhaustive search approach to knapsack problem is as given. In the exhaustive search approach to knapsack problem, all the subset of the items are generated. So the number of subsets generated for n element set is 2 power n. Hence, approximately 2 power n operations are required for generating all the subsets for solving the knapsack problem using exhaustive search approach. Hence, the time complexity of solving knapsack using exhaustive search approach is big omega of 2 power n. The traveling salesman problem. The traveling salesman problem finds the shortest tour through a given set of n cities that visits each city exactly once before returning to the city where it started. In other words, we find the shortest Hamiltonian circuit of the weighted graph. The Hamiltonian circuit is defined as the cycle that passes through all the vertices of the graph exactly once. Let us solve the traveling salesman problem using the exhaustive search approach. Let us solve the traveling salesman problem for the undirected weighted graph given here. The graph given here consists of 4 vertices A, B, C and D with weights associated with the edges connecting them. Let us consider the solution to the traveling salesman problem for the tours starting at A. In the exhaustive search approach, we find all the tours that are possible starting at A. There are 6 possible tours starting at A. And these tours are as given here. The length of each tour is the sum of the edges that connects the vertices along the tour. The most optimal length are obtained for 2 tours. The first tour starts at A, proceeds to B, then to D, then to C and back to A. And the second tour starts at A, proceeds to C, then to D, then to B and back to A. Solving the traveling salesman problem by exhaustive search approach requires n-1 permutation of cities. Hence, the time complexity of solving traveling salesman problem by exhaustive search approach is big O of n factorial. To conclude, let me summarize the topics discussed in this presentation. The major topics were the brute force approach and the exhaustive search approach of algorithm analysis. Selection sort and bubble sort were discussed under the brute force approach. The graph traversal algorithm, the knapsack problem, and the traveling salesman problem were discussed under the exhaustive search approach. Thank you.